And so I gave you the homework, linearized gravity, but I will actually discuss most of the things today. If you pay attention, of course, I will not give all the details, which I want you to actually give me, but if you pay attention, that most of the questions will be actually answered today in the lecture, so it shouldn't be that difficult. Of course, the first calculation is a little bit, it's not that long. It's okay. Anyway, so yesterday we discussed the Einstein-Hilbert action, which is the action for gravitational field itself without the absence of matter. And it's this really, really beautiful action where you say that the simplest possible scalar you can form out of the metric and the first derivatives and second derivatives of the metric is simply the Ricci scalar. And then what else it could be that this is the right answer for deriving the gravitational equations. And so it can be actually shown that if you write anything else, if you write any other scalar in 4 dimensions, then you are violating the requirement that the resulting equations are second order equations. And so this answer is actually unique in 4D. So in higher D, you have many more options. You have these low log gravities. So you can start adding some additional curvature terms. But again, there's a unique prescription for how to do it in order to get second order equations of motion. So you cannot write anything which is arbitrary. So anyway, so once you vary this, after throwing away the nasty boundary term, what you really get out of this is the simple vacuum Einstein equation that the Einstein tensor vanishes. So that's what we have done yesterday. So now we want, the aim for today is to couple to matter, and so to derive the full Einstein equations. Okay, and so this task is very, very simple because now we know how to deal with matter in curved space. That's what we discussed 2 lectures ago, and then we know how to deal with the gravitational field. So we simply just put the 2 actions together. So now the action will be matter plus gravity is simply the Einstein-Hilbert action, Einstein-Hilbert plus the matter action. And so I'll put this alpha m here just to confuse you, d4x square root of minus g, and the Lagrangian for matter. And so the way how I defined the Einstein-Hilbert action is that I put this prefactor 1 over 16 pi g. Of course, what this prefactor is really telling you, so there will be a relative ratio of couplings, whatever stands in front of Ricci scale and whatever stands in front of the matter Lagrangian. And so that, of course, tells you how strongly things couple to gravity, right? So how strong is the coupling? And so actually to capture that, how really the matter couples to gravity, I'll capture by this coupling constant alpha m. But you'll see that, of course, I define this 1 over 16 pi g so that alpha m is 0. Alpha m is 1. Okay, so now this is the action. This is the coupling of matter to gravity. Tells me something about coupling of matter to gravity. Well, and then if you vary this with respect to the metric, so the variation with respect to the metric, S, of course, has to be equal to 0 by the action principle. So we know already what the variation of the Einstein-Hilbert action gives me. And so it gives me d4 of x square root of minus g, and then 1 over 16 pi g, g mu nu, delta g mu nu. So that's what we derived yesterday. And then you have to vary the matter action with respect to the metric, but it's precisely how we defined the energy momentum tensor. So this is that. So it's minus 1/2 alpha m g mu nu delta g mu nu. Okay, so Just remember how we define the energy momentum tensor. We define it as a variation of the matter action with respect to the metric. Well, the whole thing has to be equal to 0, so I can take this must be true for any delta g mu nu. And so you are immediately getting the equations that g mu nu equals to 8 pi g alpha m g mu nu. Okay, so that's the corresponding Euler-Lagrange equations. And then you have to fix this alpha m. So this is, some coupling, some constant, showing how strongly the gravity couples to matter. And the way how to fix this alpha m, so we will see that alpha m is equal to 1. And this is by performing the Newtonian limit, by comparing with Newton. So we know that in the weak field limit, this has to, and for static fields and so on, this has to reduce to the equation, the Abba square phi is 4 pi g rho. So it has to reduce to Newton's equation. And so that fixes alpha m equal to 1, as you will see later today. So just wait for this. I haven't proved it. But anyway, so once we fix alpha m equal to 1, we have these beautiful Einstein equations. G mu nu equals to 8 pi g Newton, and then T mu nu. These equations were derived by Einstein and Hilbert. Einstein and Hilbert a little bit earlier, but anyway, in 1915. And these are probably the most beautiful equations in physics whatsoever. And the reason I'll tell you. Okay. Are there any questions so far? Easy peasy, right? So it's one-line calculation, and we arrived at the Einstein equation. Okay, so a couple of comments are ahead of us. So first one is the consistency condition, which is what basically Einstein used to actually arrive at these equations. But he used it the wrong way. He used it as a guess principle. Like he was guessing the equations, and so he guessed that this guy better be conserved. So I'm looking for a tensor which is conserved. So nabla mu g mu equals to 0. But of course, the other way around is the right way. So I have the Einstein equation. So start with Einstein equation and apply the covariant divergence on it. Okay, and then apply nabla mu on this. So it's a covariant divergence. Okay, so I have the left-hand side will be nabla mu g mu nu, but this is equal to what? That's equal to 0 because that's the Bianchi identity. So this is 0 identically. So this will be true. It's simply an identity. So for any metric, whatever I can imagine, I can form whatever the metric. I plug it into the, well, I find the corresponding Einstein tensor out of this metric, and then I calculate the divergence, and it will always be 0. So for any metric, this is an identity. Okay, so what it implies is that the right-hand side also better be 0. Better also be 0. Because if it's not, then the Einstein equations are inconsistent, right? So I have some identity, which is my, well, I have some equation, and then, yeah, it must be still true. So better also be 0, and so we are learning that nabla mu T mu nu equals to 0 is a consistency condition. for, the fact that you write down the Einstein equation. So this is the right way of reasoning. It's not the other way that I know this has to be true, so that's why I'm finding that tensor. It's not that. That's not right. That's guessing. But what is right is once I write this down, this thing automatically follows. Okay, so the consistency condition automatically follows. But we already know that this thing actually is not really a conservation of energy or conservation of momentum or something like that. But we have seen an explicit example of the perfect fluid where I've shown you that this thing actually is an equation of motion for the matter. We derived the Navier-Stokes equations out of this conservation of energy momentum tensor. So this is an equation of motion for matter. You've seen that explicitly for perfect fluid. You can show it for other energy momentum tensors. Whether that's true generally, it's still not clear. It's still a subject of research. Whether if I write any t mu nu, then this equation will give you always the equations of motion. That's not clear. And there may be some supplementary conditions which actually, but anyway, it really restricts the motion of matter quite significantly in any case. Okay, so this is definitely much more than just a continuity equation. Okay, so if that is true, then actually the Einstein equations are much more powerful than, for example, the Maxwell equations. Okay, the Maxwell equations, they are simply the field equations, and they tell me if I have the sources, what are the corresponding fields. Okay, but in order to know how my sources actually move inside electromagnetic field, I have to supply Lorentz force law. However, here I'm saying basically the Lorentz force law follows already from the Einstein equations. So this is like really beautiful. So Einstein equations play a double agent role. And so, first of all, they tell space-time how to curve. In the presence of matter. Which is the standard field equation role. So this is like field equation role. But also, as their consistency condition, they require this nabla mu t mu nu equals to 0. So they also, at the same time, tell matter how to move. In the curved space-time, curved space, which is the equation of motion role. It is because of this double agent role that really you need only one set of equations and they tell you everything. They tell you the geodesic equation, they tell you Navier-Stokes equations. Sometimes they tell you the Maxwell equations. So because of this double agent role, I think these are really the most beautiful equations. They give you everything. All right. Are there any questions? Okay.
If you take like time-independent solutions, will that thing become a conservation something, or you still get?
If you take, I'll discuss that later. Just wait 15 minutes or something like that. I'll show you. Okay, so we have this. So now let's look at this. How many equations do we really have? So similarly, so when we write down the Maxwell equations, we are getting actually 8 equations. But we know that 2 of these 8 equations are actually not evolution equations. They are constraints. So similarly, is it true that some of these equations are actually not true evolution equations, that they are constraints? And so naively, we might think, okay, so we have the metric has 10 components. G mu nu is symmetric, so it has 10 components. We have 10 equations for these 10 components. So far, so good. So G mu nu is symmetric, D mu nu is symmetric. Everything is so this should be fine. But you remember that actually you have this diffeomorphism invariance. So you can actually always perform some coordinate transformation. And this coordinate transformation, so we have 4 coordinate transformations. And so what you should really have, so this is one way to count. This is just like really only 6 components matter. Okay, so this is like having 6 E and B's, right? So in the Maxwell equations, I have only 6 things, but I have 8 equations. So now we have, but we have 10 Einstein equations. So that immediately tells you that actually, if I can always get rid of 4 components of the metric, but I have 10 equations, I better have only 6 evolution equations. So this suggests that I have 6 evolution equations, evolution plus 4 constraints. So is this true? And actually, you can think about it that way. So really, out of these 10 equations, 4 will be constraints. They don't have. So what I mean by constraint here, so Einstein equations are second-order differential equations for my metric. And so I will call an evolution equation if this is an equation which has 2 derivatives with respect to time of the metric. Okay, so they contain d square t of the metric, and if they don't contain d square t of the metric, they don't contain 2 derivatives, I will call it a constraint. So I actually allow here to be 1 derivative of the metric, and just okay, whatever. So I allow this. But I will only call evolution equation if it depends on 2 derivatives. Well, this is vague, so let's not write this. So anyway, evolution equation has to have 2 derivatives of the metric. Okay, so now the question is, can I show that out of these equations, really 4 equations don't contain 2 derivatives of the metric? So can I show that? And the statement is yes, and it follows from whatever is already written on the blackboard, and that's the Bianchi identity. So look at Bianchi identity. And then we choose, one of the components. Let's call it time. So let's call mu equal to 0 equals to t. So I'll be so the 0 component I'll call time. So this arbitrariness in choosing whatever the time is, of course, tells you that no matter what coordinate I choose, there will always be 4 equations which don't have 2 derivatives with respect to that coordinate. So anyway, so now my Bianchi identity is 0 equals to nabla mu g mu nu. So now I can choose mu equal to t, and so we'll have, this is nabla t gt nu plus nabla I gi nu. Okay. And then I can expand whatever this thing is really in terms of the partial derivative and the Christoffel symbols. So I'll have partial derivative. So this is dt of gt nu. And then I'll have two Christoffel symbol terms. And it's plus gamma t mu g mu nu plus gamma nu. Hopefully this is correct. I'm just copying down t mu. And then I still have the term nabla I gi nu. All right. I just wrote down this term explicitly in terms of the Christoffel symbols, and this I'm just leaving as it is. So now if you look at these three terms here, okay, and if you look at them carefully, they contain just g mu nu in them, but this guy doesn't have any, it's not differentiating g mu nu, it has only first derivatives with respect to time. This can have at most first derivative with respect to time. I'm not differentiating with respect to time this g, and this only gives spatial derivatives of my g mu nu. Okay, so these things have at most second order derivatives of my metric, right? Because I'm doing spatial derivatives. So my g mu nu in principle depends on two derivatives of the metric, and all these terms, they are either taking spatial derivatives of that, or they are not taking any derivatives of that. So this will at most have two derivatives of the metric. Okay, but the first term here is actually explicitly differentiating with respect to time. So now if gt nu were such that it already did depend on two derivatives of the metric, then the first term is differentiating once more. So that would produce three derivatives of the metric. So then dt gt nu actually has three derivatives of the metric. So far, so good? Okay. So the statement is, if this guy had two derivatives, now I differentiate one more, then I would have three derivatives. Plain result, right? Okay. But so assuming that this is true, this guy would have three derivatives with respect to time of the metric. But these guys have only two derivatives. But the whole thing is an identity. Identity means that all the terms have to cancel each other so that I get zero. Right? So this is true for any metric whatsoever. So no matter what the metric I put in, all these terms, when combined together, they have to cancel. They have to cancel. So I would have to be canceling now three derivatives of the metric with respect to time with terms which I know contain only two derivatives of the metric. And that's impossible. Okay, so this is impossible. And so what it tells you is that gt nu, so gt nu actually can contain at most first derivative of the metric, but not two. This cannot happen. Isn't this beautiful? So now we proved that gt nu, well, they at most have one derivative of the metric. They cannot have two. But of course, gt nu equals to 8 pi g tt nu are four Einstein equations. So we just proved that these four Einstein equations don't have two derivatives of the metric. And they cannot be evolution equations. They are constraints. So the intuition is right. and follows from something as simple as the Bianchi identity. The Bianchi identity is very, very important for everything in GR. Does it make sense? Are there any questions to this? All right. No questions? Does it make sense? Who's not happy? Everybody's happy. Perfect.
Sorry.
Yeah?
So now, if you're... So the other components can still depend on two...
Yeah.
Metric, just not the first time.
Just not the GT new.
Oh, okay.
Yeah, but there's 4 components of those, right? And they correspond precisely to 4 Einstein equations. So all what you have proved that is if you call nu equal to 0 t, then these GT new things, well, GT new Einstein equations will not have 2 derivatives of the metric in them. And so they are not true evolution equations. Of course, the counting of how many evolution equations and how many constraints you have is much nicer when you actually split space-time into time and space, and then you do Hamiltonian analysis. So then in Hamiltonian analysis, you will find that actually all you have to do is that in order the Einstein equations, so then it really tells you I specify my t equal to constant slice, and that's where I formulate my initial value problem. And so all you have to do is that you specify the 3 metric on this slice, and then you specify the derivative of the 3 metric on this slice, and that gives you actually how many? So 6 over 2, so probably 6. Yeah, thanks. All right. So the proper way to do it, like really where you see explicitly what's going on, is the Hamiltonian analysis. But already the Bianchi identity tells you that you have to have 4 constraints. All right. So let me finally return to this conservation laws. And so, again, looking at this equation, nabla mu t mu nu equals to 0, which is the consistency equation of the Einstein equations, it's necessary so that the Einstein equations can be written down. And so I said that they are already, these are something like equations of motion for matter. But at the same time, this is very similar to the special relativistic version, t mu nu equals to 0. But we know that in special relativity, this thing implies the conservation of energy, conservation of energy and momentum. In fact, what it actually means is that you can write down 4 currents. So there's this index nu, which is free, and then so you can plug nu to be 0, 1, 2, 3. So in fact, you can write this as I have a current which I call so I have J mu current, and I call it nu, and I call this T mu nu. And so you have nu equals to 0, 1, 2, 3 are 4 different currents, are 4 different currents. Each of them satisfies d mu j mu equals to 0, and each of them gives me a conserved quantity, and that conserved quantity will be either energy or momentum. So this gives the energy, and the momentum is conserved. Okay, and so of course, in order to define the corresponding, so you have this conservation of the current. So let's say current 0 gives you the energy, and current I gives you the momentum pi. Okay, so the fact that this gives some conserved charges, of course, is the same argument as we did for the conservation of the electric charge. all you have to do is that basically you have to use the Stokes theorem. Well, you have to define what the conserved charge is. In the simplest way, it's just J0, or is this G mu integrated over some spatial surface. And then you turn this divergence equation by using the Stokes theorem to some surface integral. And you say if there's no flux through the boundary, then actually whatever is here equals to whatever is there, and the charge is conserved. Okay, so that's the argument here. So now why this thing does not give me any conserved charges? So this thing does not give, in general, any conserved charges. Can you see the reason? That's a statement. So why is this? Why this thing does not give me any conserved charges, and this one does? Okay, any suggestions? Huh?
Because you have the Christoffel symbols and you cannot use the Stokes theorem.
Exactly. So last reason. So reason. Thank you so much. So reason why the general relativistic version doesn't give. So you can split the reasons into the mass reason and into the physics reason. So you just gave me the mass reason. So mass is there is no Stokes theorem for covariant derivative of higher rank, not symmetric, not antisymmetric, symmetric tensors. So, namely, there is no way. So there is no way I can do T mu nu in integral to turn it into some surface integral. Surface integral. This simply doesn't exist. There's no corresponding mass which would allow you to do that. And the reason is the Christoffel symbols. The Christoffel symbols screw things up. And this is true for symmetric tensor. Our T mu nu is symmetric, and so then there is no corresponding Stokes. So no Stokes exist. No Stokes exist. It's not that the people didn't find it, it simply doesn't exist. Okay? You can show it that it doesn't. This is not true if you had a vector. For vector, you can still have a Stokes theorem, and so if you had a conserved vector, conserved current, even if this conserved current is just covariantly conserved, this will define a conserved charge. But for a two tensor, which is symmetric, there is no such Stokes theorem. Okay, so that's the mass reason why this doesn't define any conserved charges. Now, what is the physics reason? Do you really expect the energy momentum tensor of matter to be conserved? So physics, what do you think?
It's analogous to the electromagnetic case, because where we have to add the energy of the electromagnetic field.
Very good. Now that's the answer. So remember, I place a particle in a gravitational field, but my T mu nu describes only the energy of the particle without the energy of the gravitational field, right? So it doesn't describe really how the energy changes as I add the gravitational field. So physics is that we don't expect the energy of matter alone to be conserved. So only the total energy of matter plus gravity can be conserved. Does it make sense? Makes sense, right? So if I want conservation of particles in the electromagnetic field, I also, this will not typically be conserved. I have to add the interactions with the electromagnetic field and calculate the total energy. And the total energy of electromagnetic field plus my charged particle will be conserved, but not separately. And this is also true for gravity. Okay, so we have two reasons why nabla mu t mu nu equals to 0 cannot give me any conservation. Okay. So by the way, you might think, and I'll only touch this because we may have time to discuss it next week a little bit more, but probably not, is that, well, you may think, okay, so if I expect that the total energy will be conserved, so I should be able to actually take T mu nu of matter and then T mu nu for gravity, add them together, and then write down the conservation law, right? So the question is, can I add energy of gravity and find something which is conserved, which if I add energy of gravity and then I add it to the energy of matter, this should be conserved. So now the answer is that, yeah, perhaps, maybe, but it's very, very difficult. And the reason is that people actually still don't understand what energy of gravitational field means. Okay, so this is problematic. And I will just draw the corresponding table, which maybe convince you that this is problematic, or maybe it doesn't. Let's see. So, and I will just draw an analogy with the Maxwell field. Okay, so let's draw an analogy with Maxwell. So what would you expect to call energy of gravitational field? And so in one column I will have Maxwell field, and in the other one I will have gravity. Okay, and so you already understand that we have some fields here. So the fundamental field for Maxwell, well, is the four vector potential A mu. But let's just do electrostatics, right? So the analogy is actually enough to do with electrostatics. So then I don't have the A vector, but I only have the electrostatic potential. Static potential here. Okay, and then of course in gravity the corresponding field is my metric G. Then you can form out of this field the strength, and so the strength is whatever the electric field is. So it's like, so E proportional to gradient of phi. And here, of course, the strength of gravity, well, not really, but it's given by the derivative by the Christoffel symbol. This is something like G of G. Okay, so now I'm differentiating the metric. Here I'm differentiating the field. Okay, so now what is the energy density in the Maxwell case? So energy if you study the Maxwell theory, is something like 1/2 E squared minus B squared. So E squared. Okay. So the energy, let's call it, so energy goes like E squared, so it goes like nabla phi squared. So that's the energy of electromagnetic field in the static case. So now, by drawing this analogy, the energy of the gravitational field expected to be just gamma squared. Okay, so that's the energy. It's actually, as we shall see next week, maybe this is a very, very precise analogy. You'll see that it's really what you should be calling the energy of gravitational field. But you immediately see a problem. So gamma is not a tensor, right? The gamma is not a tensor. I can get rid of gamma by going to the freely falling frame, right? So I can always get rid of the derivatives of the metric. So now, what it means is that there won't be any energy to the gravitational field once I go to the freely falling frame. On the other hand, there may be some energy if I'm not in the freely falling frame. So where is the energy stored? Where I can localize the energy? And so actually the statement is that the gravitational energy cannot be localized, and at that gravity behaves. So this is the first hint that gravity. So this is not a tensor, which of course is a problem. And so it tells you that gravity actually cannot be localized. The gravitational energy cannot be localized, and that gravity is, and you have heard that, probably is holographic. So actually people know how to define the energy of the space-time by actually going to asymptotic infinity and calculating how much energy is stored in the whole space-time. But it doesn't make sense to tell you at this point of the space-time there is some energy of gravitational field. You just cannot localize the gravitational energy because this is not a tensor. And the only things which is reasonable to tell you is like I surround my space-time, the whole space-time, by some ball, and then I calculate the energy inside. And that's the way. That's things people can calculate, like the total mass in the space-time, but they cannot tell you there is that much energy in this point of space-time. Okay, so it's just I'm only touching this, but of course this can be done a little bit more precisely. Questions? All right, so then how do I actually go back from nabla mu t mu equals to 0 to my conservation law in the flat space-time, right? So I know that in flat space-time I have conservation of energy and momentum, but now I'm telling you in curved space I don't have energy and momentum conserved, and I have problems with localizing the gravitational energy and so on. So the question is really, do we expect in any curved space-time to be anything conserved? Okay, so that's the biggest question. So the question is, do we really expect anything to be conserved? Oh no, conserved in general space-time. So what is the answer? Do we expect the energy to be conserved in any curved space?
I don't think so, because like curvature will give a source of energy, which will spoil the conservation.
Okay. Okay. So you said I don't think so. I agree with that. So remember that we have conservation laws, described by Noether's theorem, and they tell you the Noether's theorem tells you if I have a symmetry, I have something conserved, right? But the general curved space-time has no symmetry whatsoever, right? So I have just curved space, curved manifold. There's no symmetry. If I move this direction, it completely changes. I move that direction, it completely changes. If I do whatever thing I do, there is no symmetry. So general space-time has no symmetry. Has no symmetry. And so by Noether, it cannot have any conserved charges. So no conserved charges. So this is something, So all of particle physics always bases on the fact that you have some nice representations of the Lorentz group, and then you have all these symmetries of the flat space, and then you can classify particles. You lose all of that once you are in curved space. So the notion of the particle doesn't make any sense in curved space, basically. So all you will be learning in QFT doesn't make sense once you are in curved space. Okay, and then you have to modify all the concepts, basically. You have to modify what it means to be a particle, and you will see that actually it depends on the observer. Some observers will see particles, some observers will not see particles, and so on. So actually the basic concept, you have to redefine them if you are in curved space. So there are no conserved charges, but okay. So now let's say I have a symmetry. So symmetry of space-time is described by what? We had a tutorial yesterday. By a Killing vector is described by Killing vectors. So whenever I have a Killing vector, I actually have some symmetry. So for example, I have the time-like Killing vector dt. That tells me, well, my space-time is static and it doesn't depend on time coordinate. And of course, if I have such Killing vector, I would expect the energy to be conserved. Okay. So similarly, if you have space-like Killing vector which corresponds to translation, I expect that the momentum in that direction will be conserved. Okay, so Killing vectors. So let one such exists. So then I know that it satisfies the Killing vector equation psi mu equals to 0. So I have this at my disposal. Okay, and then let's use this for something. So use this to write a current, and so I'll define J mu to be T mu nu psi nu. Okay, so this is my energy momentum tensor, T mu nu, and this is my Killing vector. I just contracted one index in between them, and so I get a vector J mu. Okay. So this is my definition of a new object. So now let us calculate what nabla mu on J mu is. Okay, so let's calculate what the divergence of this vector is. Well, I have two terms, so it's nabla mu T mu nu. So I differentiate with the first one, and then I can differentiate the second one. So it's plus T mu nu nabla mu psi nu. Very good. So the first term is what?
0.
Is 0 because of conservation of energy momentum tensor, nabla mu T mu nu equals to 0. What about the second term? Is 0 because this guy is symmetric. So I can equally symmetrize over mu and nu here. But it's precisely my Killing vector equation. Okay, so this guy is 0 because of this equation here. And so this current is now conserved. So now you have a conserved current, which is covariantly conserved, but it's an object with one index. Okay, for object with one index, that is the Stokes theorem. So now, happily use the Stokes for objects. Happily, how I write it, happily use Stokes to find the corresponding charge. Okay, so if you have asymmetry in your space-time, then you are always able to find corresponding conserved charge. So if the space-time is static, the energy will be conserved. But only if you have that symmetry. General space-time doesn't have any symmetry, and so nothing is conserved. That's why nabla mu T mu nu equal to 0 cannot give you any conserved charges unless there is an extra symmetry. So now you can check that if you take T mu nu of a point particle, then whatever the conserved charge you get here is precisely the conserved charge which we studied for the geodesic motion. So if you consider a geodesic particle and you find the corresponding T mu nu, you find the corresponding current and the corresponding charge, and this charge will be precisely given by u mu psi mu, where u mu is the tangent vector to that particle, as we discussed yesterday. So this would be a specific example of this. But of course, this is much more general. This is for any T mu nu. So what you discussed yesterday was for particles, geodesic particles, but the statement is this is for any T mu nu. Okay, that's a disaster. Questions to this? Does it make sense? Yes?
Could you just give the precise statement of when you use Stokes' theorem?
Oh, so the Stokes theorem, the precise statement is that it works for vectors, or it works for completely antisymmetric tensors. So if I had, something which were completely antisymmetric in all indices, in other words, it works for forms, right? And so vector is just a special example of a form. So for forms, you have Stokes theorem, but only for forms, not for symmetric objects or for any general tensors. And T mu nu is symmetric, so it doesn't work for T mu nu. All right, so now one more thing which I want to discuss regarding the Einstein equations is actually, whether we can always solve them and what kind of solutions you may expect to get. And this is related to the topic which is rather controversial, but many people did their PhDs on that, and many basic results in general relativity actually assume these things. So the last thing I want to discuss is energy conditions. Energy conditions. And so you might think that one way to solve the Einstein equations, G mu nu equals to 8 pi G T mu nu, is the Poo's way. So Poo's way of solving the Einstein equations, So Poo is the bear of little brains. So he may think, okay, so I want to solve G mu nu equals to 8 pi G T mu nu. So I take any metric whatsoever. Okay, so take any metric G. Okay, plug it here. So calculate the corresponding G mu nu. Okay, whatever you find, you just call that T mu nu, 8 pi G T mu nu. So whatever comes out. And then I have a solution of Einstein equations with that corresponding T mu nu. Okay, so that's the Poo's way of solving Einstein equations. In fact, not only Poo is using this, but also, people still use it until today to find some interesting solution. So whatever metric I want, it will be a solution of Einstein equations, provided that I define the T mu nu to be whatever is on the left-hand side. Okay, very good. So now this allows people to construct. This allows people construct stupid things like wormholes, warp drives, and so on. Okay, so whatever I want to get, if I want to get a wormhole, well, I'll write the metric for the wormhole, just plug it into the Einstein equations, and I find the corresponding energy momentum tensor, which is the source of this. Or I can form a warp drive, or I can do anything. So if you've watched Star Trek. So, but the problem is that found, in this way obtained T mu nu, so found T mu nu is typically crazy. And so what I mean by crazy is that, so you know that T mu nu has some general structure. The 0,0 component is the energy density or something like that. And then the 0I component is the energy flux, or the momentum flux, and whatever stands in the ij component is the pressures and so on. And so, it's basic requirements to say, well, for example, my pressures better be positive. Okay, why should I have negative pressures? What does it mean to have negative pressure? My energy density better be positive, right? Why should I have negative energy densities? That doesn't make any sense. My flux, energy flux, better be moving on time-like curves. It shouldn't be moving on the space-like curves, because if it's moving on the space-like curves, it travels faster than speed of light. Okay, so such T mu nu is crazy. So now to avoid this, people impose some reasonable requirements as to what T mu nu has to satisfy. And these reasonable requirements are called in energy conditions. So more precisely, they are called energy conditions. Okay, and so one such energy condition, for example, would be an weak energy condition, which is the simplest. Well, and I see that I won't help you much with the homework, but okay. So an example would be the weak energy condition. Okay, and that simply says that whatever the T mu nu I have, T mu nu, if I contract it with T mu and T nu, where T mu is any time-like vector, then this better be positive. So if you look at it, if I take T mu nu to be 1, 0, 0, 0, what you are saying is that T0, 0, which is the energy density, has to be bigger or equal than 0. So I cannot have negative energy densities. In fact, if you do it not only for T mu, which is just 1, 0, 0, 0, but for all T mu, which is time-like, then you get actually conditions that the energy density is positive, but also the energy density plus pressure. You can have three principal pressures, Px, Py, Pz, and so these have to be positive as well. So these are the consequences of the weak energy condition, that the energy density is positive, but also those are true. Okay, so that's an example of an energy condition. And then you have many more energy conditions. So for example, you have null energy condition, you have strong energy condition, you have dominant energy condition, and so on. And so all these energy conditions, they tell you some reasonable assumption about what the energy momentum tensor should look like. Okay? Yes?
That energy, the weak energy condition, these T mu nus, so you are considering all time-like curves.
Yeah, you consider T mu to be any time-like vector.
For example, when we are solving Einstein's equation, if we do it the right way, that we consider T mu nu like from a physical...
Some physical reasonable source, yes?
Which coordinates do we use to...
Oh, very good. So this is an invariant statement, right? So I'm saying this is coordinate invariant statement. So this is a scalar, right? For given t and for given t, this is a scalar, and I can calculate in any coordinates I want. So typically, so these things are valid in some orthonormal frame where I can sort of diagonalize my T mu nu. So I just introduce an orthonormal frame. My T mu nu looks like I have rho here and P1, P2, P3, and whatever, and that's it. so then you are getting such a condition here. So this is, of course, a coordinate-dependent statement, but I can make it coordinate-independent if I discuss in the orthonormal frame. Okay, but this the definition is definitely coordinated. Okay. So anyway, so I have all these possibilities. I have the weak, I have null, strong, dominant, many more. So then the question is, where do they come from? Where do they come from? Is there any fundamental principle telling me I have to have these energy conditions? Okay, so now you may start probing, right? So, okay, very good. So these are some conditions on the matter. Okay, we have theory of matter. That's quantum field theory. Okay, so now I know that if I'm to search where these energy conditions come from, I better search quantum field theory books. So now I look at the one which has everything, which is the Weinberg's book. So now you start searching for weak energy condition in the Weinberg's book. And you go from page 1 to page 10,000 or whatever, and you don't find any weak energy condition. Okay, so then you can actually go and seek the word weak energy condition, and it's not there. So actually, what happens is that these conditions are not property of matter. They don't follow from any quantum field theory. So they are not property of matter. So not property of matter. Not property of Q of T. Rather, they have to be telling you, well, these are the reasonable assumptions. What happens when the matter interacts with gravitational field? So rather how matter interacts with gravity. So then you maybe start, looking. So what is the fundamental principle which fundamental principle implies these energy conditions? And there is no such fundamental principle. So this is really something which people consider reasonable. And so what reasonable matter should satisfy, it gives you these various energy conditions. But the truth is there is no really any fundamental reason why the matter should satisfy these things. Okay, and so there is no fundamental reason. But the problem is that once you throw away these energy conditions, anything is possible. You can form warp drives. You can form wormholes. You can have anything you want. So actually, maybe in the nature there is something telling you that although there is no fundamental reason for these things, maybe something is telling you I have to have something like this. Otherwise, anything is possible. Otherwise, I can use Pooh's way to solve the Einstein equations. So the last question is: are they satisfied? Are they satisfied? And the answer is, for reasonable solutions, yes. But as well, at the same time, you have many examples which people consider to be well-founded physics, and nevertheless, they violate these energy conditions. So for example, the answer is no. No in general. And one example you will see very soon is the inflation. So if you really believe that there was an inflation period in the early universe, then this thing, for example, violates the strong energy condition. Another thing is that Hawking proved, is his famous area increase theorem, is that if you have a black hole, the area of the black hole will, whatever it will do, whatever the matter is thrown in, will always increase. The black hole is always getting bigger. Okay, so now this requires the null energy condition. So, however, then he also shown later on that actually the black holes evaporate. they produce the Hawking radiation, and they get smaller as they produce the Hawking radiation. So certainly the Hawking radiation has to violate whatever the condition he imposed for the area increase. So Hawking radiation has to violate the assumption of the theorem that the area of the black hole is always getting bigger. So this is not true, and so this violates the null energy condition, which is, by the way, the only one which really people believe should be always satisfied. So now they replace this with this average quantum null energy condition for quantum matter, but it's not clear whether that's satisfied. So anyway, so there are these reasonable assumptions, but maybe the assumptions are not so reasonable after all, because some well-founded physics actually violates these assumptions. But if you get rid of these assumptions completely, then anything is possible, and you don't have any predictive power for the theory. So then you can have warp drive, and then you can have wormholes, and then you can have all the nonsenses there are. Okay, so I thought that's like nice to say. Questions?
I have a question.
Yes.
And how do people get this T mu if we don't know how how fields or matter in general couples to gravity?
Aha. So you are asking, well, for example, for inflation, right? So inflation is like a paradigm. It's not one theory. It's just a framework of theories. And you say, I need my universe to be doing this, so that I explain some problems which we see in the universe, like flatness problem or whatever. And so then you can start. So this is the assumption. So I just need the universe to be doing this. So then the question is how to make the universe be doing this. And so, for example, the simplest theory of inflation is that I have some scalar field, and that's slowly rolling, and it sort of mimics cosmological constant and whatever. So now I have a concrete realization of inflation theory, and then I can check, and then you can check, are the energy conditions for that satisfied? And they can't be satisfied. Okay. Actually, so for scalar field, certainly not satisfied, but in general, you can show that any inflation theory will violate some energy condition. Right. But simply, if you want the universe to be doing this, this is not allowed by the energy condition. So you may take that as a sign that the inflation is a wrong idea, and Neil would be happy about it, but but actually, many people believe that inflation is the right idea. All right, so now we have 20 minutes to solve your homework. So DE, Newtonian and post-Newtonian expansion. So by the way, please take the homework. It's somewhere here if you haven't got it yet. So we have two equations. So start with, let's say, the geodesic equation and the Einstein equation. G mu nu equals to 8 pi dt mu nu. And the geodesic equation, d square x mu d tau square plus gamma mu alpha beta dx alpha d tau dx beta. Okay, and so let's look at various limits of this thing here. So in the first instance, what I haven't really shown you that there was this alpha m here, and I said this alpha m will have to be equal to 1 in order this equation reduces in the Newtonian limit to the Poisson equation. So that's what I want to show you now. But of course, then you can go beyond the Newtonian limit, then you can include some relativistic effects, and then it's quite interesting to see, what this equation looks like if I, for example, still consider weak fields, but I consider relativistic effect, and similarly here. Okay, so let's now take the Newtonian limit of this. Take like the zero order Newtonian limit. And then you take the first order approximation, you take some relativistic effects, And then you take second order and third order and whatever. And so when people study, for example, the black hole collisions at this point, and they want to predict whatever the LIGO sees, like the gravitational waves, they go to, I don't know, 7 post-Newtonian order. So we will only discuss the zeros and the first. But actually, in order to, whatever is being observed now, in order to explain that, people go to 7.5 post-Newtonian expansion, whatever. So these are called post-Newtonian expansions. And people go quite high now in order to explain whatever is observed in LIGO. Okay, so let me start with doing a linearized gravity. So that means, of course, these equations here are equations for G mu nu, but they are nonlinear. And as such, they are hard to solve. So what people do is that they linearize them. So they take whatever the coordinates are, the right coordinates, but they say we are almost flat plus a small perturbation. And by saying that it's small, we just neglect everything of the order of 8 squared. Okay. So if this is true, then as we discussed last week, this must be true. If you raise the indices, you just simply pick up the minus sign because the correction is of the order of 8 squared. You just multiply these two matrices and you get that it's delta as it should. And that means that if I want to calculate the Christoffel symbols, G mu alpha beta, then I'm differentiating the metric. But if I differentiate this guy, I get 0. So the only thing which I can differentiate is the h. And so that's already linear in h. So I can put a flat metric here, eta mu sigma, and then h sigma beta alpha plus h alpha sigma beta minus h alpha beta sigma. Okay, so that's what your Christoffel symbol is. And then if you want to calculate the Riemann tensor, let's call it Riemann. Well, it's d gamma minus d gamma plus gamma gamma minus gamma gamma. Okay, so you see that the Christoffel symbol is already linear in h. So this guy is already linear in h. So gamma gamma will be quadratic in h. So this term is not gone, it's gone, and that term is gone. And all you have to calculate is derivatives of the Christoffel symbols, and you will do it in your homework. And so once we have the Riemann tensor, we can also find the Ricci tensor by constructing the two indices, and you can also find the Einstein tensor. And so there's a couple of steps missing, which you will fill in your homework. But basically, the calculation, I'm doing the whole calculation here. So then you find the expression for the Einstein tensor, and you'll see that it's quite complicated. And again, to make it simpler, you better introduce new variable. So this new variable, let's call it h mu nu bar. So that's a new variable. And in this new variable, the thing actually simplifies. And so what it is simply h mu nu minus 1/2 h eta mu nu, where h is the trace of h mu nu.
Sorry.
Yeah.
Which metric do we now use to raise and lower indices?
Aha. So what do you think? For example, this one here.
Eta would be the most convenient, I guess, but I don't know.
Precisely. Why not? This is already small. This is already of the linear order in h. I'm expanding everything only to the linear order. So what I mean by this is this h mu nu eta mu nu. right? Because this, if I did include G, there would be already quadratic correction, and I throw it away. Thanks for that question. So now equivalently, you can write this as H mu nu. The old one is the new one, H mu nu bar. And I hope I have the sign right. Let's hope this is true. H eta mu nu. Where again, this is a trace of my H bar. So this is my new variable H mu nu bar. Okay. So once you introduce this new variable, your expression for the Einstein tensor simplifies. It gets actually basically like the expression shortens by half, but you still have some terms. Okay. So the next step is actually, so this already simplifies Einstein tensor, Einstein to something like 1/2 size, which is good, but it's still, you have still some terms. So the next step is to actually use the gauge symmetry of gravity. So you derived yesterday that if I change the, and so of course the gauge symmetry of gravity is just the fact that I can use diffeomorphisms, like I can use any coordinate transformations. So you derived yesterday that if I can go from x mu coordinates to x mu, now I will put a minus sign because I think that's the correct sign. So I still don't know what is the origin of that minus sign in the tutorial yesterday. But anyway, so I do a coordinate transformation. I do take the old coordinates are now x mu minus xi mu, where xi mu is a vector, and I treat it as small. I don't write epsilon here. Then you've shown up to a sign yesterday that h mu nu transforms as h mu nu plus d mu psi nu plus d nu psi mu. Actually, you've shown that the delta g alpha beta has covariant derivatives here, but again, covariant derivatives and the partial derivatives in the linearized version are the same, because the difference is the gamma terms and times the vector. Vector is small, and the gamma term is also small, so that's the order of 0.08 square, and I'm throwing that away. So that's why now I have the partial derivatives here. Okay, so you've shown this yesterday, and so what you haven't shown, but what you will show in your homework, is that this allows to fix a gauge, sometimes called harmonic gauge or the Dondes gauge, or you know, this the same gauge actually has many names, and that is so similar to electromagnetism, where you are imposing d mu a mu equals to 0. So now I'm imposing d mu h mu nu bar equals to 0. So that's my gauge. So compared to d mu a mu equals to 0 in the electromagnetic case. Very good. And so once you do this gauge, and you will explicitly show that you can do it, then the Einstein equations actually simplify drastically. So then you'll find that the Einstein tensor is simply minus 1/2 the flat box operator partial alpha on h mu nu bar. Okay, so now you have only one term for the Einstein tensor. And so your Einstein equations, linearized Einstein equations, are simply box on h mu nu bar equals to minus 16 pi g d mu nu are the linearized Einstein equation. Isn't this beautiful? So again, you know, you started with something which is highly nonlinear, and then you linearize that, and you arrive at something which is like the wave operator acting on something h mu nu equals to my source t mu nu. Of course, if I switch off the source, if t mu nu is equal to 0, then I have just box on h mu nu. But because this is a wave operator, you immediately expect gravitational waves. Okay, so even in the absence of sources, I will have gravitational waves. So Einstein was really excited that yeah, we predict the gravitational waves, and let's measure them. And then he calculated the next day what is the power expected for this gravitational wave, and he got really, really depressed because it's like really, really teeny tiny, right? And so he thought that this will never be measured, and that we will never observe gravitational waves. But in fact, 100 years after he discovered them, we actually observed them, right? So it took 100 years to get the precision for measuring gravitational waves. So of course, you know immediately the solution of this equation. So the solution of this equation is, again, because this is a linear equation with the right-hand side, so it's a special solution with the right-hand side. But if you look at that equation, it's precisely what we had in electromagnetism. So the solution must be retarded potential, right? So now I take the green function, which is the retarded potential, and then instead of J mu for the Maxwell field, I'll just plug T mu nu, and that will be my solution for a special solution solving this equation. And then the most general solution of this is solution of the homogeneous equation, which are basically the waves, plus this special solution which I find by retarded potentials. So you immediately know the solution of linearized gravity. So just a note, and again, I don't know if we'll have time to discuss this next week. We shall see. So let's say I switch off the sources. So T mu nu equals to 0. So then we have two equations to solve. We have the equation box on h mu nu equals to 0, and then d mu h mu nu equals to 0. So this is my gauge condition, and this is my wave equation. And so so these are the equations for some field in flat space-time, right? So we are really expanding around the flat space-time, around the flat metric, and this is some field which lives in that space-time. And this is these are the field equations for spin to particle in flat space. As formulated by Pauli and Fierce. Okay, so if you just want to write down a field theory, classical field theory for spin to particle in flat space, these are the equations you would write down.
How did they knew that it was a spin to?
Okay, so what spin means is basically that you are asking how the field behaves under the rotations or something like that, or how it responds to rotations. So it comes from how this corresponding field will respond to rotation. I don't want to discuss it now. It'll take the whole lecture, but yeah. But you know, one way to look at it is that people know now that whatever is a vector field, if you describe your field by a vector field, it will give you spin 1. If you describe by a spinor, it gives spin 1/2. If you describe by a symmetric tensor, it gives you spin. Okay, so that's how string theorists approach that now. Whenever I find symmetric tensor, it gives me spin 2. But maybe we'll discuss it a little bit more next week. I'll see. Okay. So, however, so notice. So what this is telling you is that perhaps general relativity is just a theory of spin to particle at the linear level. So now going back to the Einstein equations, which are nonlinear, is that telling you maybe the spin to particle actually interacts with itself. So there must be a self interaction of the spin to particle somehow, and so that in the end you get, at the nonlinear level, you get the Einstein equation. So of course, the interpretation of gravity as a spin-to-particle theory is only valid in flat space, right? Only then I can decompose the metric into the flat metric plus the perturbation. If I have general curve space, high curvature, and whatever, the split doesn't make any sense. And then the interpretation of a spin-to-particle really doesn't make any sense. So really you can give a precise meaning to this only if you are close to flat space. All right. Questions?
Yeah.
Yeah.
Provided that this T mu is okay with the energy conditions, can you put like any T mu you want there, like a lot of energy there, or it would be not?
Sorry, that's the question towards the energy conditions.
No, towards.
Here.
Perturbing Minkowski.
Here. Of course, what I automatically assume here is that the T mu is small, okay. Because if T mu were like really, really strong, I wouldn't have the linearization valid. Yeah, so T mu has to be really like a small perturbation of nothing. Okay. Yeah. Okay, so now structure of T mu. So we are close to the flat space, and so that's why the structure actually makes sense. So the T mu, in general, I was telling that today many times, but the 0, 0 component is the energy density, and then, so that's the 0, 0 component, and then there will be energy flux here, energy flux here, and then because this has to be symmetric, there's also energy flux here, and then whatever, so this is the 0I component, and then IJ component is the pressures and stresses, so pressures. Okay, so now you can start thinking about the limit which we want to do. So we have the weak field, and so we satisfy these linearized Einstein equations. But in order to have the Newtonian limit, we better say, well, my sources actually move quite slowly, right? So that's when the Newtonian limit is valid. And also, remember when we discussed the Navier-Stokes equations, we were receiving terms like rho plus p, but I told you that p is suppressed by the c square. So the pressure actually is typically really, really small for non-relativistic matter. Okay, so in other words, the Newtonian limit will be such that the pressure is 0 and that the energy flux is 0. So in the Newtonian limit, the only component which survives out of T mu nu is just the energy density. So Newtonian limit. Of course, we have to have the weak field. That's why we linearize the gravity. But the T mu nu is simply rho and then 0 everywhere else. So the only thing which is non-trivial is the energy density. Okay. The fields are static. And so then if you look at this equation here, then the box operator just becomes a Laplace operator because the field is static. So field is static. Field is static. That means h mu nu divided by 0. Well, time derivative of h mu nu is 0. And so then we have the 0, 0 component gives me Laplace on h 0, 0 equals to minus 16 pi g, and then t0, 0, which is rho. So in order this to be true, of course, we also know from the geodesic equation that h0, 0 is something like minus 2 phi, 1 plus 2 phi. So I can define phi to be minus 1 over 4, why is it 0, 0, which gives me that g0, 0 is whatever we had before, minus 1, minus 2 phi. So I just can plug here phi. I just call this h00 bar to be phi. And then you recover that Laplace on phi. Laplace on phi equals to 4 pi g rho, as you should. Setting alpha m equal to 1. Remember, we set everywhere alpha m equal to 1. If I do this phi. But then also, you have other components of the Einstein equations. So you have also Laplace on h, whatever, 0i bar equals to 0, and Laplace on h ij bar equal to 0. So these are your other equations. So now, provided that you impose some boundary conditions at infinity so that the solution doesn't blow up and at infinity and so on, these have trivial solutions. So then tells you h0i bar equals to 0 and hij bar equals to 0. Okay, so the only non-trivial component is really this h00 bar, and it gives you g00 is minus 1 and 2 phi, and it gives you that g0i are 0, and it gives you that gij are 1 minus 2 phi dot ij. You can check that by using, so when, you have to translate it to h mu nu through this equation here. So we have the bar quantities, which are related to my unbar quantities h mu nu by this thing here. And the statement that this only non-trivial bar quantity is phi translates to that hij is minus 2 phi and h00 is minus 2 phi here. All right. So this is the Newtonian limit. So really in the Newtonian limit, you have the metric like this. This is what I gave you a long time ago. And this is what you use to study the gravitational redshift of the satellite. But it comes from solving these equations and assuming that only the energy density is non-trivial. That's the Newtonian limit. Of course, the geodesic equation gives you that A is minus gradient of phi. You can go beyond the Newtonian limit, as you will do in your homework. And so the next step is that you say, well, the sources actually may move a little bit. So I will have some current here. And if you have some current here, you will see that this electrostatic equation, the Poisson equation, will suddenly become something like a Maxwell equation. So the linearized Einstein equations will give you the Maxwell equation, basically. And the geodesic equation will give you something like Lorentz force law. Okay, so you will see that basically gravity sort of knows about electromagnetism. It's called gravitomagnetic effects. And you are getting basically something like Maxwell theory out of Einstein equation. So that's your homework, and you may be looking forward to it. And so the next week we will start gravitational waves. Are there any questions? Okay, so see you in the afternoon.